Our goal is to train and evaluate robots in simulation. But how can we capture the diversity of the real world inside a physics simulator? We built SceneSmith, a system that generates simulation-ready indoor environments from natural language, dense, physically valid, and immediately usable in any major robotic simulator. SceneSmith decomposes scene construction into a hierarchy of stages. First, a layout stage generates architectural geometry, walls, doors, room connectivity. Then, each room is independently populated through furniture, wall-mounted and ceiling-mounted stages. Finally, supporting surfaces, tables, shelves, counters, spawn their own branches for placing small, manipulable objects. Every stage is driven by 3 coordinated VLM agents. A designer proposes changes using structured tools. An independent critic evaluates the result, checking semantic plausibility, physical feasibility, and prompt alignment. An orchestrator manages iteration and can roll back to prior checkpoints if quality drops. Here is the critic in action. Over multiple rounds, the designer refines its placements based on the critic's feedback. The scenes improve as objects are repositioned, added, or adjusted. Let's watch the scene come together. The designer agent works entirely through tools. It renders the scene to observe its progress and places assets one by one. Crucially, the designer isn't limited to a single action per turn. It can invoke arbitrarily many tools, observing and refining until it is satisfied before handing off to the critic. When the designer needs a new object, an asset router directs a request to the right strategy. A teddy bear is generated on demand via text-to-3D. A storage cabinet with doors is retrieved from an articulated object library. And an area rack is created as a thin covering, a lightweight textured surface. Every asset is validated before being returned to the agent with automatic retries on failure. For text-to-3D, we first generate a reference image and segment the foreground. Then, we reconstruct a textured 3D mesh and scale it to target dimensions. Finally, we augment it with collision geometry and VLM estimated physical properties: mass, inertia, and friction. The result: open vocabulary scene generation that handles everything from yoga studios to hotel lobbies, each populated with dozens of objects in realistic arrangements. All SceneSmith scenes are fully simulatable. Here, we shake the entire scene. Every object responds to physics, sliding, toppling, and colliding with its neighbors. And these scenes export to any major simulator. Here is the same environment running in Drake, IsaacSim, and Muchoco. To demonstrate the usefulness of these scenes for robotics, here we teleoperate a robot directly in our generated environments, interacting with the objects, opening furniture, and navigating the space. SceneSmith enables many downstream applications. As one example, we demonstrate automatic robot policy evaluation. Consider a robot that should set the table, not just in one lab kitchen, but in any kitchen. Testing this in the real world means renting dozens of Airbnbs. With SceneSmith, we can generate thousands of different kitchens that all satisfy the task prerequisites and evaluate policies across all of them automatically. Here is how it works. We start with a task description. For example, pick a fruit from the fruit bowl and place it on a plate on the dining table. An LLM generates diverse scene prompts that satisfy the task prerequisites, each with different layouts and object configurations. SceneSmith builds all of these environments. A robot policy then executes in each scene. And finally, an evaluation agent inspects the result, using simulation state queries and visual observations to verify whether the fruit actually ended up on the plate. Across all scenes, we get an automatic task success rate. No handcrafted predicates are needed. Here, a robot policy is running across our generated scenes. Some succeed, some fail, and the evaluator agent correctly identifies which. SceneSmith dense, physically valid, simulation-ready environments from text. We believe environment generation is no longer the bottleneck for scalable robot training and evaluation in simulation.